All right. First example on page 442, number 10. If they have them already set up in an integral or a definite integral, then you know you have the area set up correctly. You know in this interval the secant squared of the x is going to be larger than the cosine value of x. They have it set for us. Also, we're going to know in that interval that the secant squared of x is going to be always existing. In other words, it's a continuous function. It's not got an asymptote. It's not got a break. It's not got any of those things in it. If they set it up for us, it's that way. Now, if they don't set it up for us, then we may have to check those pieces of information out. We want to have functions that are continuous to be successful.
So what are they not?
Really, if they're not, we're going to have to break it up into two separate intervals, separate pieces, doing the parts that are continuous. And make a note that it's not continuous at this spot. Okay, so we have this information. Now the question is, do we recall the antiderivative of the secant squared of x dx? And looking at some of your tests, yes you did, and some of you, no you didn't. If you know correctly that the secant squared of x produces the tangent of x, you're doing good. What is the antiderivative of the cosine of x? So then that becomes plus the sine of x evaluated between negative pi over 4 and positive pi over 4. To evaluate the secant, you do 1 divided by the cosine. To evaluate the secant squared, you do 1 divided by parenthesis cosine of x, close parenthesis twice, and then square. All right. So, we passed through class. We had the unit circle quizzes. You remember. The exact value of the tangent of pi over 4 is? The exact value of the sine of pi over 4 is? And then we subtract. The exact value of the tangent of negative pi over 4 is? The exact value of the sine of negative pi over 4 is? So basically, oh yeah, by the way, that was an even function. We could have just doubled what it was between 0 and pi over 4, and we'd been all right. There's symmetry about the y-axis with this image.
Well, we did not do that.
No, we didn't do that, so we're going to be okay anyway. So then we have 1 plus the root of 2 over 2 plus 1 plus the root of 2 over 2. You get that value set twice. So 2 plus the root of 2. And yes, I would find that to be an acceptable answer. Now, if you were going to go out and paint a wall that had that much area, you'd probably want that to be 3.4, or 3.14, no, 3.414. That might make more sense to us. Questions about doing this problem? Okay. Now for the second popular question. Everybody done? Same page. Next popular question happens to be 28. And I think you'll see why it's popular here in a moment. What kind of function is this? It's a function of y instead of x, correct? Which means our calculator is set up to deal with functions of x can't graph this.
Why can't you just move it over?
Because it doesn't quite work that way.
Can you change it?
Why? We can just graph it by hand. We're smarter than the average bear. We got to be able to do that.
We could also
The average bear couldn't graph. Like, even a smart.
That's why I said we're smarter than the average bear, so we can.
Graph that.
Nice try.
A smart bear cannot graph that. You know what?
human cannot graph that.
What do you mean a human cannot graph that? I can graph that, no problem.
Smart human cannot graph that.
bear.
You're insane.
A smart
Oh, I am
bear
not.
cannot.
Yes, Mr. Richter, you want to graph a function of y by hand, and I'm sure you enjoy it.
Y equals.
That's beside the point.
No, that makes you insane, which is exactly my point.
So it's at.
Okay. It is different in a thought process of how do we graph these functions of y? What does it really mean? So we need to think about this and say x is equal to y over the square root of 16 minus y squared. Just like when we do f of x, when it's f of y, now it's x is equal to that instead of y equals that. So we can have things that maybe loop back around and it won't be a function in terms of a vertical sense, but it will pass the horizontal line test. When it's g of y here, it's thinking about in terms of x equals 0. When it's y equals 3, that's just y equals 3. So some of these pieces, especially the two pieces here, represent either a horizontal or vertical line. So you just have to remember which one. So the y equals 0, that is actually a vertical line, and it's not there. And it is going to be right here. This is g of y equals 0. That's where it's located. That's a boundary line. We also have y equals 3. What kind of line is the line y equals 3? Okay? What color do we want for this line? How about we not do white and do something else? Red.
How many lines did you use?
Okay. So we have those two parts, and those are going to be, in a sense, parts of our boundaries. So as we're working on things, we need to expect this curve to come back in and touch somewhere there a second time. So now we think about when you have x equals y over 16 minus y squared, let's think about how we might do that. Is it okay if I let y be 0 to begin the graphing process here? Could y be 0 in this problem? So 0 divided by 16 minus 0 squared, and then the square root of that is what answer?
0.
So that tells me that this point right here is one of the points that's going to be on this curve. Now I want to ask myself the question, what happens if y happens to be 1? So I get 1 over the square root of 16 minus 1 squared, or 1 over the square root of 15. Well, approximately, where is 1 over the square root of 15? Can we do the fun thing about decimals here?
0.25-ish, 0.26.
0.25, 0.26. So when y is 1, we've just barely moved this way. Question for you, what is different about y being negative 1? Is it just going to be negative 1 over square root of 15? So it's down here. The problem is I probably closed this thing back in here, so I probably won't need it. But there's some symmetry that's happening here. I probably won't need that piece, but there's symmetry.
I don't like that.
What happens when y is 2? 2 over the square root of 16 minus 2 squared. This is 2 over the square root of 12. And the square root of 12 is 2 root 3, so just 1 over the root of 3, which is root 3 over 3, which sounds familiar from unit circle people. Yep, about 0.58. When y is 3, 3 over square root of 16 minus 9. Or 3 over the square root of 7. What is 3 over the square root of 7? So when y is 3, we're out here at 1.3, and we have this curve, looks something like that. So our region in question is something like this region in here. But these are functions of y, not functions of x. So the rule's a little different. Functions of x, we had top curve minus bottom curve that we were dealing with. So if I tried to deal with a top curve minus bottom curve, I might get somewhere, but I'm going to have to know the exact number that's right there. But when they're functions of y like this, we can take the antiderivative from the start to the end of right minus left. Nope, not dx, dy. So on the right, which is farther or larger than what's on the left, this is another way of looking at this, but this time it's when you're dealing with functions of y. That's why I like this question. I can tell you're thrilled by it. So what is the equation of the curve that's on the right? Yeah, this one, right? That was what we used to make that blue line. So the area is going to be the antiderivative. We'll get to the what to what here in a second. But the right side is y over the square root of 16 minus y squared. What's on the left side of this little thing? Under what set of y numbers am I doing this process? Yeah, 0 to 3. So do you understand how we built that definite integral?
Can you just re-say that again?
I'm dealing with the curve that's on the right, so this part right here that came from this y over the square root of 16 minus y squared, minus the curve that's on the left, which happens to be the green dashed line there, which was the 0. And then the numbers here are the y numbers where I'm working. So I have a y number starting at 0 and a y number that ends at 3. That's my boundaries. Now I'm hoping that this one looks kind of familiar to you. So the area is the antiderivative from 0 to 3 of y over 16 minus y squared, the square root, dy. If it did not have the y in the numerator, it would be something like an arc sine concept, but it's got the y in the numerator. So it's a whole different animal. We know that we need to let a u equal the 16 minus y squared. What is du? Negative 2y dy. I have in this numerator the y and the dy. What do I not have? So negative 1/2 du is y dy. And so my area is now going to be the antiderivative from an a to a b of negative 1/2 over the square root of u du.
Why didn't you do the 16's a squared and y squared?
Because I didn't use an a squared and a u squared because I recognized with that extra y, it's not the same pattern. But that's one of those hard things. That's what we struggled with on our last test a lot. So a is equal to negative 1/2 antiderivative from a to b of u to the negative 1/2 du. Guys, not every single question that's got something in the denominator is an ln. This is not an ln. We were way too fond of ln's on our tests. This one here, if I increase that power by 1, what does it become? u to the positive 1/2, and then I multiply by the reciprocal of that power, so multiply it by 2, and I evaluate that from the a to b. So I end up with the square root of 16 minus y squared evaluated between 0 and 3, and the 2 and the 1/2 multiply to a 1. It is still negative. Thank you. That'll be important in a minute. Yeah, it's still negative. The negative from this 1/2 is still there. I just didn't carry it, unfortunately. So now we get negative the square root of 16 minus 3 squared minus the negative of the square root of 16 minus 0 squared. So this one is negative square root of 7 plus the square root of 16, which is 4 minus the square root of 7 units squared. Or whatever the decimal approximation of 4 minus the square root of 7 is. And that's units squared. Any questions about that?